Let's move on with the visual and intuitive topology subsection of the topology playlist. And this particular video focuses on topological properties, which we began to see in previous videos. So, topology, as we know, studies properties of spaces that remain unchanged under continuous deformation. And when we say deformation, we're talking about things like stretching, bending, compression, and even twisting. So a useful way to understand topology is to ask, what features of a space survive? Stretching, bending, twisting, provided we do not tear or glue the space. So tearing and gluing are not allowed topological actions, like I keep saying. So several properties are especially important. We have ideas like connectedness, that talks about whether a space consists of one piece or several pieces. Then we have holes. Holes talk about missing regions or non-trivial loops that distinguish spaces from one another. Like in a cylinder, we have a hole in the center, right? And we have dimension, the number of independent directions needed to move locally. Then we have boundaries. These are points where a space locally looks like a half space rather than ordinary Euclidean space. And there is orientability. This talks about whether a consistent notion of clockwise or counterclockwise or clockwise slash counterclockwise orientation can be maintained through the space. Then compactness. Informally, it talks about whether a space is finite in extent and does not have points escaping to infinity. That talks about compactness. Compactness. So these properties help us classify and compare topological spaces. For example, a sphere and a torus are both connected. Compact, two-dimensional surfaces without boundary. So a sphere, a torus, they are connected, they are compact, they are two-dimensional surfaces, and they don't have boundary. However, they differ in their number of holes. So a sphere has no holes, while a torus has one handle. So topology therefore replaces questions such as how long is this curve? What is its angle? What is its exact shape? With questions such as is it connected? Does it have holes? Does it have a boundary? Can it be oriented consistently? Is it compact? What is its dimension? So these properties provide some of the fundamental language of topology. So let's go ahead and talk about connectedness as we get on. So connectedness describes whether a topological space is made up of one piece. So a topological space X is connected if it can be written as a union of two non-empty disjoint open sets. Equivalently, X is connected if there do not exist non-empty sets U and V such that X is equal to U union V, with U intersection V being empty. So you have two disjoint sets whose union gives a particular set. Then you say that set is connected. That space is connected. So the set U and V would form a separation of X now. So if you can bring U and X together to form U and V together to form X, then they form a separation of X. And then we say X, the space X there is connected. So the intuitive meaning of that is this. Imagine a rubber object. If you can separate it into two pieces without cutting it, then it was not connected, right? So without cutting, you can separate into two pieces. Then in that case, you say it is not connected. If the entire object must remain together unless you physically tear it apart, then you say it is connected like that. So examples, the closed interval 0, comma 1 is connected because the real line R, of course, we also know that the real line R is connected. Then the circle S1 is connected. The sphere S squared is connected. So all these are connected. By contrast, we see that 0, 1, union 2, 3 are disconnected, right? They are disconnected. So this is disconnected because it consists of two separated pieces. Then similarly, if you have minus infinity to 0, union 0 to infinity, it's also disconnected like that because in both sets, 0 does not belong to both, right? So let's talk about path connectedness. A stronger property is path connectedness. So a space X is path connected if for every pair of point X, comma Y belonging to X, there exists a continuous function gamma, which like the closed interval 0, 1 mapped to X such that gamma of 0 is x, and y gamma of 1 is y. In other words, we can continuously travel from one point to any other point while remaining inside the space. So we have a good example in a circle. So you can keep transforming, you can keep stretching the circle out until you get an ellipse. Or in fact, you can get uh, different ellipses with different cross-sectional diagonals or something like that until you get to the very end of that. So you can, it means you can move all the way from gamma of 0, which is x, down to gamma of 1, which is y. So in other words, we can continuously travel from any point to any point while remaining inside the space. So just like a circle, right? For if you put any 2 points on the circumference of a circle, you can draw any line. You can draw a line still following the path of the circle, still following the circumference to join the 2 points. So every path connected space is of course connected. So however, in general topology, a connected space need not be path connected. So a connected space does not have to be path connected, but if it is path connected, it is automatically connected. For many familiar spaces studied in elementary topology, however, connectedness and path connectedness behave similarly. Important distinction, they're talking about connectedness. Can the space be separated into two pieces? So that's what connectedness asks. But path connectedness asks, can I draw a continuous path between every pair of points? So any two pair of points you draw in the space, you can always join them together. So like that. So in that case, you say it is path connected. So path connectedness therefore gives us a stronger way of being connected. So talking about connectedness, imagine you have you're considering A, let's consider A, which is 0, 2, and B, which is 0, 1, union 2, 3. Determine which set is connected. So the set A, which is the closed interval 0 to 2, is an interval in R. So it is an interval on the real line. So every interval R is connected, as we know already. So every interval, like rather in R, is connected. Therefore, we say that A is connected. Now, if you consider B, which is the closed interval 0, 1, union 2, 3. So there's a gap between 1 and 2 like that. So we can separate B into two non-empty sets. So this B, uh, we can separate it into 0, 1, and B2, we can separate this B now into 0, 1, and 2, 3. So since the two pieces are separated, then B is automatically disconnected. Thus, we say that A is connected while B is disconnected because there's a jump between 1 and 2. Then the topological lesson we learned from here is that the exact lengths of the intervals are irrelevant to connectedness. So what matters is whether the space can be separated into two distinct pieces. This illustrates an important principle of topology. Connectivity is qualitative rather than metric. So it's not about the length, it's about whether it's connected or it's not connected. So to demonstrate the example of 0, 1, 2, 3 that is disconnected, so we can use this Python code you see here. So if you do this now, we end up getting, you see the connected line 0 to 2 is connected, whereas 0, 1, 2, 3 are disconnected because there are no overlaps. So there's a gap between 1 and 2. So we say 0, 1, union 2, 3 they are disconnected, while 0 to 2 is connected like that. So the first set contains every point between 0 and 2. This is what you see here like this. So it forms one piece. The second set has a gap between 1 and 2, like here. So it consists of two separate components, 0 to 1 and 2 to 3. So the connected components of 0, 1, union 2, 3 are precisely 0, 1, and 2, 3, though each of them is connected, but their union is not connected because there's a gap between 1 and 2. So it would have been connected if we probably had 0, 1, union 1, 2. That would have been connected easily like that. So in that case, there wouldn't be any gap here. So let's talk about holes. I haven't talked about connectedness. One of the most intuitive ideas in topology is the concept of a hole. So a hole is a feature of a space that cannot be removed by continuously deforming the space without cutting or gluing. So the word hole has different meanings in different dimensions. So it is useful to distinguish them carefully. So let's talk about zero-dimensional holes first. Disconnected components can be viewed as a type of zeroth order topological information. For example, x equals 0, 1, union 2, 3 has two connected components. So this is connected, this is connected. This information is captured by the zeroth Betti number. So beta naught of x is 2. Then a connected space has beta naught of x is 1. So for a connected space, the beta naught of X, the Betti number is 1, but in this case, the beta naught is 2 because you have beta naught for two different connected spaces coming together in a union. Then we have one-dimensional holes. So one-dimensional holes. A circle has a one-dimensional hole. Consider S1, which is the collection of xy belonging to R squared, such that x squared plus y squared is equal to 1. So a loop traveling around the circle cannot be continuously shrunk to a point while remaining on the circle. So a loop traveling around the circle cannot be continuously shrunk to a point while remaining on the circle. This is the essential topological distinction between a circle and a filled disk. So a filled disk is a closed disk, by the way. That is, instead of equal to 1, you have less than or equal to 1. So this disk now, d squared, which is the collection of xy belonging to R squared, such that x squared plus y squared is less than or equal to 1, has no one-dimensional hole because every loop inside the disk can be contracted to a point. Now, we also have two-dimensional holes. So the sphere S2 encloses a three-dimensional region and is associated with a two-dimensional homological feature. So the distinction between different types of holes becomes increasingly important in algebraic topology. So let's talk about Betti numbers. It's been coming up a lot. So a useful way of counting holes is through Betti numbers. Very roughly, beta naught counts connected components, beta 1 counts independent one-dimensional holes, beta 2 counts independent two-dimensional holes, higher beta k counts higher dimensional holes. For a circle, beta naught is 1. So for a circle, that's the so beta naught is 1 and beta 1 is 1 for a circle. Then for a sphere, beta naught is 1, beta 1 is 0, and beta 2 is 1. Then for a torus, beta naught is 1, beta 1 is 2, and beta 2 is 1. So the torus therefore has two independent one-dimensional loops and one two-dimensional. So the torus has two independent one-dimensional loops and one two-dimensional homology class, like that for a torus. So the important warning here is that the everyday word whole should not be treated as a single precise mathematical concept. Topology distinguishes wholes by dimension and by the algebraic structure used to detect them. So this leads naturally to homology and homotopy theory, which provide rigorous ways to study wholes, like that. So, I mean, for this circle, right, this beta naught here counts connected components. So the circle has just one connected component, the circumference, and beta one counts independent one-dimensional holes. That's only one hole inside the inside the circle. That's why beta 1 is 1. For a sphere, right? So there's only one connected component. I mean, the whole surface of the sphere. But then you have beta 1, which counts independent one-dimensional holes. So there's no hole in the sphere. And then beta 2 counts independent two-dimensional holes, like that. So, and that is actually 1. That is, if you look at the space and the space enclosed, the have beta 2 to be 1, like that. So we then have circle versus disk. Compare the circle S1 with the closed disk D2. Are they topologically equivalent? So first of all, consider a loop on the circle. Take the loop, gamma of t is cos 2 pi t sine 2 pi t, and t goes from 0 to 1. This travels once around the circle. There is no continuous deformation that shrinks this loop to a single point while keeping the entire deformation inside S1. Thus, the loop represents a non-trivial hole, like this for a circle. But then if you consider a loop inside a disk, so inside d squared, the same loop can be continuously contracted because it is less than or equal to 1. So you can have, in fact, the radius can be 0. It can also be 1. So because it's less than or equal to 1, so you can keep shrinking that. Although for the circle, you can't shrink it. So inside d squared, the same loop can be continuously contracted. Define h of s comma t to be 1 minus s cos 2 pi t sine 2 pi t. Of course, there are similarities between a disk and a circle, right? The only difference is the fact that for a circle, x squared plus y squared is equal to 1, but for a disk, it is the x squared plus y squared is less than or equal to 1. So if it is a closed disk, it's less than or equal to. If it is an open disk, you have less than 1. And as a result of the fact that of the less than part, you can continuously contract the same loop inside the disk. So in this case now, S and T that we have here all lie between 0 and 1. So at s equals 0 now, we have h of 0t and 1 minus s. That's 1 times the whole of this. So cos 2 pi t sine 2 pi t. So it's not like a circle. So this is the original loop now. As s is 1, so the same disk is shrunk to the center 0, 0. We are going to demonstrate that using Python code pretty soon. So h1t will then be 0, 0. So it means that the same disk has now been contracted into the center of the original disk. Therefore, the loop contracts to a point inside a disk. The conclusion here is that the circle and disk are not homeomorphic, because the circle, you cannot shrink it, because the radius is always 1, or whatever the radius is fixed. But for a disk, it can be less than or equal to the radius, or I mean in this case 1. So the essential reason is that S1 being a circle has a non-trivial one-dimensional hole, whereas this 2 does not have that kind of hole. This is a central example of how topology distinguishes spaces that may look geometrically similar. So circle and disk look geometrically similar, but they're not homeomorphic, meaning that they are not topologically equivalent, as a result of the fact that you cannot shrink a circle because the radius is fixed, but you can shrink a disk inside the same loop because the radius is less than or equal to 1. So let's look at this Python example. So it's the same formula and equations we have up there. That's what we are using here. So I'm just going to show the code on the screen in case you need to look through. So we just define the x circle, y circle. You have 2 cos pi t, then sine 2 pi t, cos 2 pi t, like that. Then we do for s values, you take values from 0 to 1 like that. And because s is t and s, vary from 0 to 1 like that. And then you draw the closed disk. So for the closed disk, you have cos theta, sine theta, that way, and then you draw the boundary circle. So the circle, so at some point, at some point the disk corresponds with the circle at the point where the radius is exactly 1 for the disk also. So you have that correspondence. But apart from that, while the disk can be shrunk into the center, the circle cannot be touched like that. So then we draw the boundary circle here, and then we then, so you test showing the contraction parameter, so all the various values. Then you configure axis. Then you have the homotopy right here. Then this is the update loop now, then current point on the loop. So the fact that that can also be changed. So we then have the HTML animation to JS HTML. So if we run this now, see what we get. Okay, I think it takes a little bit of time to get reproduced. So yeah, I think it's done now. So you see this circle right here. So the circle is actually S1. I mean, it's blue, but at this point in time, when you still have the full disk, it coincides with the disk. But guess what? We can animate this to see what happens. So if you press play here, you see that now the blue circle is there. You cannot do anything to that because the radius is fixed. But for the disk can take, because it is less than or equal to 1. So it can, when the radius is 1, it's here. As the radius is reducing, it's like going into the center. And that is where at 0, from what we had up there for the math, right? At 0, where is that now? Did it come later? Yeah, here. So at 0, you have cos 2 pi t sine 2 pi t. That's the whole circle. But at 1, it becomes 0, 0. And that is why you see this shrinking into the origin. So it disappears into the origin like that. But a better way to even see this is we can have a static visualization of several contraction stages, so that we see a static diagram that shows how all of that is happening. So this is the code for that, but the static visualization of several contraction stages. So about the same thing, except that we now see the static contraction. So here now, as you saw up there, by the time this starts to shrink, right, you discover, no, you can see this one has contracted a little bit here. So the circle is blue right there. In the beginning, it didn't look like you could see the circle because it overlaps with the orange color. But by the time you begin to animate it, you see that the circle is then fixed, but the disk at radius 1 is orange, and then it keeps shrinking into the center. So this other one shows us everything in a static fashion like that. So here, contracting a loop inside the disk D2. So when the radius is 1, this is what you have here. So you have the closed disk D2. So the circle is also there in blue, but you can't see it because it's overlapping with the orange. So it means that at some point, the circle and the disk coincide. But the only thing is that because the radius of the disk is less than or equal to 1, so it can keep contracting inside the same d squared loop. So when s is equal to 0, that's in the beginning, you have the circle. Then when s is 0.25, you have this green circle now. Then when it is 0.5, you have this red one. When it is 0.75, you have this one. When s is 1, then you have this point inside it. So that is what was animated there, what was shrinking inside. So having talked about that, then we can then move on to dimension. A dimension describes the number of independent directions available available locally in a space. The idea is familiar from Euclidean geometry. A point has dimension 0. So if you have just a point, you have dimension 0. A curve has dimension 1. A surface has dimension 2. Ordinary space has dimension 3. So topology generalizes this idea. So first of all, we're talking about a point. You have the dimension of a point to be 0. So for a line on the real number line, for instance, dimension is 1. For a circle, which is also a curve, the dimension is 1. For a plane, you have the dimension of R2, which is equal to 2. And then for a sphere, you have dimension 2. The dimension of S2 is 2. For a torus, the dimension of T2, that's the torus, is 2. For ordinary Euclidean space, you have dimension of R3 to be equal to 3, like that. So I mean, this seems easy. For a point, it's 0. For anything in dimension, so like R1, S1, they are all 1. But once you see 2 on top of anything, the dimension is 2. And when you see 3, the dimension is 3, like that. So in three-dimensional real number space, you have 3 like this. So intrinsic versus extrinsic dimension is the next thing we get to consider. An important topological idea is that dimension can be intrinsic. A circle can be embedded in R2, but its intrinsic dimension is actually 1. So similarly, a sphere sits inside a three dimension, that's R3, but the sphere itself is 2-dimensional. So locally, a small patch of the sphere looks like a piece of R squared. So it looks like a circle. If you cut every surface you cut, you have something looking like a circle. So the dimension of S2 is 2, actually, even though it requires 3 coordinates to describe its position in R3. So dimension is topologically meaningful. A fundamental theorem of topology states roughly that Euclidean spaces of different dimensions are not homeomorphic. So Euclidean spaces of different dimensions are not topologically equivalent. In particular, m-dimensional real number system is not homomorphic to n-dimensional real number when m is not equal to n. So m has got to be equal to n for this 2 to be homeomorphic. This is far from obvious because a continuous bijection alone is not enough. So the inverse must also be continuous. Dimension, therefore, provides a powerful invariant for distinguishing spaces. So look at example 3. How do you determine dimension? Determine the dimension of the following spaces. So you have a line segment. Consider the closed interval 0, 1. Of course, it is the one-dimensional real number space. So a small neighborhood of an interior point looks like an interval in R. Therefore, the dimension of 0, 1 is 1 because 0, 1 is in the real number. In fact, the dimension of anything in the real number itself is automatically 1. So for a circle, of course, a circle is also S1. So the circle S1, which is the collection of all xy such that x squared plus y squared is 1, can be parameterized locally using one parameter, such as the angle theta. Therefore, the dimension of S1 is also 1. Talking about a sphere now, like I've given you the simple idea. So if it is a point, that is 0 automatically for the dimension. But if it is R1, S1, so R1 means just one-dimensional real number. And for a circle, which is also S1, so the dimension will be 1. So but for a sphere, once you see S2, you know the dimension is 2. So it is locally described by 2 coordinates. So for example, away from the poles, latitude and longitude provide 2 local coordinates. Hence, the dimension of S2 is actually 2 because, I mean, latitude and longitude is associated with sphere because the Earth is roughly spherical. Then you have a torus. A torus can be parameterized by 2 parameters. x is r, big R plus small r cos v cos u. Then y is big R plus small r cos v, all that multiplied by sine u. And z itself is r sine v. So here, u and v are independent parameters. Therefore, the dimension of T2 is equal to 2. So the main idea here is that the dimension of a manifold is determined by the number of local coordinates needed to describe points in the space. Thus, for a circle, the number of local coordinates needed to describe points in the space is 1. Then for sphere, you need 2. For torus, you also need 2. Then, of course, just follow the number, how it is represented. For something in real number, you just have R. For something in for a circle, it's S1. For sphere, it's S2. For torus, it's T2. So you can just follow the number and you get the dimension. So that's one hack to getting the dimension of any space very easily. So the boundary of a topological space, now we're talking about boundaries, right? The boundary of a topological space describes the points where the space stops. That talks about the boundary. For a simple interval, you have the closed interval 0, 1. So the boundary consists of two endpoints. You have the boundary of 0 and 1. You have, so 0 beginning, 1 is the end. So it starts from 0 and it ends at 1. So the interior is 0, 1 like this. So the point 0 and 1 are special because a small neighborhood around either endpoint looks like a half interval rather than an ordinary interval that way. So talking about the manifold viewpoint, for a one-dimensional manifold, interior points locally resemble R. That's more like you're dealing with something on the real number line. So boundary points locally resemble the half line 0 to infinity. For a two-dimensional manifold, interior points locally resemble R2. So boundary points locally resemble the half plane R by 0 to infinity. So examples now, you have the closed disk for d squared, which is, so it is closed because of the equality. If the equality wasn't there, it would have been open disk. So d squared equals the collection of all xy such that x squared plus y squared is less than or equal to 1. So the boundary is dd2. And the boundary for a closed disk will be like, is a circle. So the boundary of a disk is a circle. So this disk has a boundary. So for a sphere, so the sphere is S2, right? So there's no boundary for a sphere. So ds2 is empty. Then we come to talk about a cylinder. A finite cylinder has two circular boundary components. So the topology resembles. So a cylinder looks like a rectangle and it is a rectangle that is folded into a circular shape. So you have a circle and a something in the real number line like a height. So its boundary is d of s1 by 0, 1. So that is s1, s1 mapped to 0 here, union s1 mapped to this one here. Thus the boundary consists of two circles. So you have the circle at the top and the bottom of a cylinder. These are the boundaries in that situation. So thus the boundary consists of two circles. So talking about a torus now, a torus has no boundary, just like a sphere. So because it is solid all the way, so in case you've forgotten what these things look like, we have them here again. So this is a sphere. So sphere and torus, they are solid. Like it's more like you have for this looks like a football that is pumped, and then this is like a tire tube that is also pumped like that, and they have similar behavior except that the torus has a hole in the center like this. So we're focusing on these two like this. So a sphere and a torus. So we go on. So with that, for the torus, a torus has no boundary, also just like the sphere. So the boundaries of T2 is also empty, like the boundary of a sphere is empty. So let's talk about the boundary versus edge now. So in topology, boundary has a precise mathematical meaning. It does not simply mean a visually obvious edge. For example, a sphere has no boundary, even though it appears as a curved surface in three-dimensional space. I mean, if you have a globe which is spherical, you can touch it all over the place, right? And it feels like a boundary, but in the sense of topology, that's not seen as a boundary. So a sphere is a closed surface. So every point has a neighborhood that looks like r squared. So a disk, on the other hand, has a genuine boundary because points on its circular edge have neighborhoods that resemble a half plane. Then we talk about the boundary of a disk. So the boundary of a disk is simply a circle, as we already know. So consider d squared, which is less than or equal to x squared plus y squared less than or equal to 1, where x and y are both real. So we want to determine its boundary. So a point xy is in the interior if there's a small open disk around it that remains entirely inside D2. So for points satisfying x squared plus y squared less than 1, so these ones are not on the circumference of the disk. And this is possible. Therefore, the interior of D2 will always be x squared plus y squared is less than or equal to 1. But the points satisfying x squared plus y squared equals 1, which coincides with a circle, are exactly the points where the disk actually stops. So hence, the boundary of a disk will be x comma y such that x squared plus y squared equals 1. And that results to a circle. So a circle is simply the boundary of a disk. So the disk therefore has a circular boundary. By contrast, if we consider the sphere s squared xyz, which is x squared plus y squared plus z squared equals 1, then every point has a neighborhood that looks like r squared in that case. So because every point has that circular thing, has that neighborhood that looks like r2, consequently we say ds2, which is a sphere, the boundary of a sphere is actually 0 because they don't exist. So we say it's empty. So we use all the equations we've dealt with. So you have the closed disk less than or equal to, you have the interior, which is less than, you have the boundary, which is simply a circle, and we use all of that to write a code just to demonstrate that reality. So if you run this now, so maybe I'll try to go step by step. Boundary of the unit disk, you have that annotated here. So you will create a grid of point in R2. So that's minus 1.2 to 1.2 like this. Now XY creates the mesh grid, taking in X and Y. Then we compute X squared plus Y squared at every point because that's like the core. So R squared is X squared plus Y squared. Then we now have interior points satisfying x squared plus y squared less than 1. So the interior is r squared less than 1. Then we create the figure itself. Figure as this plot, subplot. Then we shade the interior. So ax contour, xy, interior as type integer. Then we have the levels of shading and all that. Then we draw the boundary. The boundary is simply the circle x squared plus y squared equals 1. And then we also do the contour. Then we draw the coordinate axis. That's, just the axis that pass through the center horizontally and vertically. Then we mark the origin. Okay, that's origin 0, 0. This is the size of the point, and with the z order. Then we annotate the interior with all these annotations now. So after all of that is done, we just we have this circle right here. So you have this. So boundary of the unit disk. So the boundary of the unit disk is the circle that encloses it. This is the interior point, the origin 0, 0. And these are the vertical lines now. So that's how that goes. Then we have orientability, having considered boundaries just now. We go on to talk about orientability. Don't forget, we are looking at topological properties. These are the things you are going to study in some mathematical depth as we progress. So orientability asks whether a consistent notion of orientation can be maintained throughout a space. For a surface, imagine assigning a normal direction to every point. If the surface allows us to make this choice continuously and consistently everywhere, the surface is orientable. If moving around the surface forces the orientation to reverse, the surface is non-orientable. So for instance, let's look at some familiar examples. Say you have a sphere. The sphere is orientable because if you move, if the surface of a sphere allows us to keep moving. So if you assign a normal direction to every point, so if you move around a sphere, the orientation does not reverse, right? You can keep going in the same direction. And that is what, so the sphere is not orientable, it's orientable rather. Same for torus, same for cylinder, same for the Möbius. But the Möbius strip is not orientable because the Möbius strip is closely related to a cylinder, except that, so imagine you take a rectangular sheet, if you fold it to get a cylinder, but for the Möbius strip, instead of folding directly, you now reverse the ends before taping them together. That's how you get a Möbius strip. So as a result of that, the direction reverses at some point. So while sphere, torus, and cylinder are orientable, the Möbius strip is not orientable. So the Möbius strip can be created by taking a rectangular strip, giving it a half twist, and joining its two ends. Although it appears to have two sides at first, it actually has only one side. So if you start at one point and move continuously around the strip, you eventually return to the starting point with your local orientation reversed. Therefore, no global consistent orientation exists here. Exists in that case. Hence, Möbius strip is non-orientable. This is the deal here. This is what a Möbius strip looks like. This is it right here. So it would have easily been like a cylinder, except that instead of it to move straight like that. So if you imagine if you keep move around, by the time you come back here, the orientation changes like that. So That's why we have that. But for a cylinder, you can just move around it and you have the same orientation all along, all the way. That's the idea of non-orientability. So the Möbius strip is non-orientable in that case. Then we talk about a sphere. A sphere can be given a continuous outward pointing normal vector. For the unit sphere, we have this formula like we've been seeing. The outward normal at xyz is simple. That's the normal to xyz. That's xyz. So this varies continuously over the entire sphere. Therefore, S squared is orientable. A torus also admits a continuous normal vector field, so you can keep moving around the torus. So thus T2 is also orientable. Why orientability matters? Orientability becomes important when defining surface integrals, flux, integration of differential forms, degree theory, Stokes theorem, orientation classes, intersection numbers. It is therefore not merely a visual property. It has deep consequences throughout topology, geometry, and analysis. So orientability is one of the key properties we study in topology. So example where the Möbius strip is non-orientable. Consider a rectangular strip with coordinates uv, for instance, where u lies between 0 and 2 pi, and v lies between u takes values from 0 to 2 pi, and v takes values from -1 to 1. So if you construct a Möbius strip using the parameterization that we are used to, of u comma v is 1 plus v over 2 cos u over 2, all of that multiplied by cos u. Then you have the next one, 1 plus v over 2 cos u over 2, all of that multiplied by sin u, and then v over 2 sin u over 2. The crucial identification occurs at the ends. So you have u equals 0 v, which is similar, which then goes to u equals 2 pi comma minus v. So notice the sign change for v. So you have v, starting from v, you end up with minus v. So you have the sign change from v to minus v. So that means that after traveling once around the strip, a local orientation is therefore reversed. So if the strip were orientable, we could assign a continuously varying normal direction, and such that returning to the starting point would reproduce the original normal. But the half twist forces the direction to reverse. Therefore, Möbius strip is non-orientable. So a physical experiment, if you take a pen and draw a line through the center of a Möbius strip, continue drawing without lifting the pen, you eventually return to your starting point, having traversed what appears to be both sides of the strip. So this demonstrates the unusual topology of the Möbius strip. So the phenomenon is not caused by the particular way the strip is drawn. It is a topological property that survives continuous deformation like that. So we can visualize the Möbius strip using this code right here. I mean, it's still the same formula as we have. So you declare your uv 0 to 2 pi, and u is 0 to 2 pi, and v is -1 to 1. And then big U and big V, it creates a mesh using the small v's. Then you declared the formulas XYZ that we saw, the 1 plus 1 over 2 v, I mean v over 2 cos u over 2, all of that. And then you just plot all of that and you get the Möbius strip like this. So it's easy to remember that it's more like you're supposed to get a cylinder, but at the point of joining the cylinder, you now fold the edges in, and gives the half twist that causes the non-orientability. So the half twist is responsible, the half twist you see around here is responsible for the non-orientability. Compare this with a cylinder. A cylinder has no half twist, and it is then orientable because the direction doesn't reverse by the time you get back to where you started from. So talking about compactness, let's take a look at the informal meaning of compactness here. Compactness is one of the most important ideas in topology. At an elementary level, compactness can be thought of as a space being bounded and containing all of its limiting points. So compactness is about a space containing being bounded and containing all of its limiting points. The intuition works particularly well for subsets of Euclidean space. For example, the closed interval 0, 1 is compact, whereas the interval 0, 1 is not compact because 0 and 1 are not parts of the space. So the real line R is not compact because it extends infinitely in both directions. So you have it is an open interval from -infinity to infinity. So you can't say it is compact in that sense. Then you have the Hahn-Borel theorem, which we already saw under real analysis, under the real analysis places, and of course the real analysis precursor to. I mean, I think that was the second video, so or the fourth video as a preparatory for what we now do. So for subsets of n-dimensional real number, the Hahn-Borel theorem gives a precise characterization that a subset of Rn is compact if and only if it is closed and bounded. So open intervals will never admit that, but closed intervals does. So the closed interval 0, 1 is compact because it is closed. This is a closed interval. 0 and 1 are included, and it's also bounded. So nothing in this set is lower than 0, and nothing in this set is bigger than 1. That's the boundary. So 0 is the lower boundary, 1 is the upper boundary. But this open set 0, 1 is bounded, though it is bounded by 0 and 1, though 0 and 1 are not part of the interval, but it is bounded by 0 and 1, but it is not compact like that. So it is bounded, but it is not closed. That's why this is not compact. So the set closed interval 0, open interval infinity at the top is closed but not bounded. So it is not compact. So the real line, so it is not bounded because of course it goes all the way to infinity. So the real line R is neither bounded nor compact in that sense. So this is bounded. I mean, this is compact because it is closed and bounded. This is not compact because it is bounded but not closed. This is not compact because it is closed but not bounded. And the real line is neither bound nor compact. So these are possible scenarios we can have for compactness. Then, why is compactness useful as a property in topology? Compactness often allows us to turn local information into global conclusions. So, for example, a continuous real-valued function on a compact space attains both a maximum and a minimum. If f maps x to the real number line is continuous and x is compact, then there exists points x minimum x min, x max that belong to x such that the function of x min is less than or equal to f of x is less than or equal to f max for every x belonging to the space x. So this is extreme value theorem. Compactness therefore compactness is therefore extremely useful in analysis, geometry, and topology. So let's see which sets are compact here. Of course, we've talked about all of these ones before. So consider the following sets of R. So A, the closed interval 0, and of course, we know this is compact because it is closed and bounded. B is not compact, though it is bounded, it is not closed. Then C is not compact, though it is closed, it is not bounded. And D is not compact because it is neither bounded nor closed. So, I mean, determine which are compact. I've given the answer. So, but I mean, set A now, A is closed. So it is closed and bounded. Therefore, by the Hahn-Borel theorem, A is compact. Closedness and boundedness imply compactness. Then the set B now, the open interval 0, 1. So it is bounded but not closed because it does not contain its limiting point 0 and 1. So that's why it is not closed, though it is bounded by those limiting points. Therefore, B is not compact. Then talking about set C, so for set C, we have it's closed interval, but it is not bounded. Therefore, C is not compact. And for set D, which is the real number system itself, it is unbounded. Therefore, D is not compact. So in summary, we see this, we see all of this that for 0, close 0, 1, it is closed, it is bounded, so it is compact. 0, open interval 0, 1, not closed, not closed, bounded, but not so that means once either of closedness or boundedness fails, then compactness also automatically also fails. So the half open, half closed interval 0 and half closed interval infinity on this side, it is closed but it is not bounded, so the compactness is not there. Then R, it's closed but not bounded, so it is compact. I think we saw the other time that R is both not closed and both are not bounded. It's neither bounded nor compact. So I think it should be no for both here. Neither bounded nor compact. So the real number system is neither bounded nor, what's that now? Neither bounded. Oh, okay. It's not bounded. I think the idea is that it's not bounded. So just one failure makes it not compact. So R is, though it's closed, it is not bounded, and then it is not compact. So the example illustrates why both closedness and boundedness are required for compact subsets of Euclidean space. So let's talk about compactness and sequences. There's another useful way to understand compactness. In Euclidean spaces, a set is compact if every sequence in the set contains a convergent subsequence whose limit remains inside the set. For example, consider the closed interval 0 to 1. Take any sequence x1, x2, x3 in between in that interval. So with xn belonging to 0, 1, I mean being a subset of this set, the Bose-Weierstrass theorem guarantees that there is a sequence xn1, xn2, xn3 that converges So because 0, 1 is closed, its limit definitely belongs to 0, 1. Thus, compactness prevents sequences from escaping the space. So for something to be compact, then it means the space it provides cannot be escaped. So compare this with the open interval 0, 1. So the sequence xn equals 1 over n lies entirely in 0, 1. But xn approaches 0. So, and 0, of course, is not part of the interval itself, but this xn is moving towards 0. However, 0 is not an element of, it does not belong to this open interval, and xn is approaching this, although the whole thing lies in this interval. Thus, the sequence approaches the missing boundary points. This illustrates why 0, 1 is not compact, because though it is bounded, it is not closed. Similarly, in an unbounded space such as R, the sequence xn equals n has no convergent subsequence in R. Compactness therefore provides a strong form of containment. So if everything in a space can be maintained in the space without anyone escaping, then you say the space is compact. So we have a Python demonstration for this, talking about sequences and compactness. We can visualize the sequence approaching a point that is excluded from 0, 1, just like that 1 over n case. So we have all of this going, and then this is exactly what happens. So you see xn is going all the way down, converging towards 0, and then the limit, of course, is 0. So we have boundedness, but no closedness, so no compactness, basically. So every term satisfies xn from 0 between 0 and 1 for sure, but the limit of xn as n approaches infinity is actually 0. Because 0 is not contained in the open interval 0, 1, the space does not contain this limiting point. By contrast, if we use the closed interval 0, 1, the limit 0 belongs to the space. So this is one reason why compactness is closely connected to completeness and closedness in Euclidean spaces. So comparing the main topological properties that we've been looking at now, the properties studied in this lesson answer different questions. So connectedness is answering the question, is the space one piece? Holes, what non-trivial voids or circles does the space contain? Dimension, how many local directions does the space have? Boundary, where does the space locally stop? Orientability, can a consistent orientation be maintained? Compactness, is the space topologically well contained? Then these properties are often used together. So consider several familiar spaces now. So we have a circle. So connected, dimension 1, boundary, no boundary, orientable, yes, compact, yes. D2, that is a disk. So is it connected? Yes. Dimension is 2. Once you see for the dimension, I mean, that's easy to know. Just know the number. Of course, 0, 1 is in the real line, so that's R1. So the dimension will be 1, 1 in that case. So D2, dimension is 2. The boundary is the circle, right? That's when the radius is, when the x squared plus y squared is exactly at 1. That coincides with the circle. So the circle bounds the disk. It is orientable, yes. It is compact, yes. And S2, which is sphere, so it is connected, yes. The dimension is 2, of course, because of the power 2 here. You can take that as a clue. Then the boundary, there's no boundary. Then it is orientable, yes. Compact, yes. Then cylinder, connected, yes. Dimension is 2. Then boundary, 2 circles. That's the bottom circle and the top circle. Then orientable, yes. Compact, yes. Then torus. Torus is connected, has 2 dimension, no boundaries, orientable and compact, yes. Then the Möbius strip, of course, is connected. The dimension is 2. The boundary is 1 circle for the Möbius strip. And then the orientability is no, because of the reversal you get by the time you try to make a trip round the strip. Then the compactness, of course, yes. Then R, it is connected, yes. Dimension is 1. Then boundary, no boundary. Then orientable, yes, but not compact because it is not bounded. So for compactness, there has to be boundary and connectedness. Then for 0, 1 union 2, 3, it is not connected. Dimension is 1 because it is still in the real line at the end of the day. So boundary, several endpoints. Orientable, yes, and connect, no. Compact, no. It is not compact because though there are boundaries but no connectedness. So the table should not be interpreted as saying that these properties completely classify spaces. Two spaces can share many of these properties and still fail to be homeomorphic. For example, the sphere and torus are both connected, compact, two-dimensional, orientable, but they are without boundary. So, yeah, they are not homomorphic because their topology contains different hole structures. So the hole in torus makes it significantly different topologically from a sphere. So this demonstrates why topology requires a collection of invariants rather than a single property. So a systematic topological comparison now. So suppose we are given two spaces X and Y. I want to know whether they could be homomorphic. A useful strategy is to compare topological invariants. Step one, compare connectedness. If X is connected but Y is disconnected, then X and Y X is not homomorphic to Y, or they are not topologically equivalent. Step two, compare dimension. If the dimension of X is not equal to the dimension of Y, then they cannot be homomorphic. So once any of these things break, you don't have to worry about the rest. Then compare boundaries now. If the boundary of X is empty, but the boundary of Y is not empty, then X is not homomorphic to Y. Then step four, you need to you can also compare orientability. If X is orientable but Y is not orientable, then they cannot be homomorphic. For example, S1 by 0, 1, which cylinder represents, is orientable, whereas the Möbius strip, which looks something close, is not like that because Möbius strip is not orientable, while cylinder is. Then compare compactness. If one space is compact and the other is not, they cannot be homeomorphic. For example, the closed interval 1 is not homeomorphic to the real number, though it is in the real number line, but this one is compact. R is not compact. So for 6, compare holes. If their homology or multiple structures differ, then they cannot be homomorphic. For example, a sphere and a torus have different homology groups. So the torus has a hole. Therefore, these spaces are not homomorphic in that case. So the important principle then is this: if a topological invariant differs, the spaces cannot be homomorphic. So once any of these properties differ in two spaces, they cannot be homomorphic. So symbolically, if I is a topological invariant and I of X is not equal to I of Y, then X is not homomorphic to Y. However, equality of one invariant does not usually prove that two spaces are homomorphic. The distinction is crucial. Different invariants implies different topology, definitely different topology, but generally same invariant does not necessarily mean same topology. So it means if you have to check all the invariants, all the properties, you have to check that they have all the properties together. But once you find one where they differ, then you can conclude that they are not homeomorphic. So don't be carried away that okay, because these two have the same particular property in common, then it's invariant. But once you see one disparity, then they are not homeomorphic like that. So we talk about sphere versus torus. Compare the sphere S2 and the torus T2. The connectedness, they are both connected because B naught of S2 is 1 and B naught of T2 is also 1. Talking about connectedness. So connectedness does not distinguish them. So you can still continue. So if they did not have the same connectedness, you would have concluded that they're not homomorphic straight. So now that you have connectedness to be the same, then you go to dimension. For dimension, both have dimension. So dim of S2, the dimension of S2 and dimension of T2 is 2. So both does not distinguish them. Dimension, though they both have the same dimension, but that is not to tell that they're actually homomorphic. So you can check boundary. So neither has boundary. So ds to dt2 is empty. That's the boundary of the sphere, and the torus is empty. It's 0. So boundary does not distinguish them still. Then you talk about orientability. Now, again, both are orientable. So just orientability does not still distinguish them. So when it comes to compactness, both are also compact. Again, compactness does not distinguish them. Then when you come to holes, then we come to the final place. Now consider their Betti numbers. For the sphere, B naught of S2 is 1, B1 of S2 is 0, B2 of S2 is 1. For torus, B naught of T2 is 1. So still similar. B1 of T2 is 2 here, now different. B2 of T2 is 1. So the B naught and B2 are the same, except for B1 of S2 and B1 of T2 that are different. So that's a crucial one. So the crucial difference is the fact that the beta 1 of S2 is 0, while beta 1 of T2 is 2. So that's the only tiny thing causing all the difference. So the fact that there's a hole in a torus and not in a sphere. Therefore, with that alone, you can say that a sphere is not homomorphic to a torus. This is an excellent example of why studying topological properties systematically is so powerful. Several simple invariants agree, but the whole structure reveals the difference. Then we have a useful summary invariant, which is the Euler characteristic. The Euler characteristic provides another powerful topological invariant. For a space with finite dimensional homology, it can be defined using Betti numbers such as chi of x equals summation from k equals 0 to infinity of minus 1 raised to power k beta sub k of x. So this is the formula for Euler characteristic. For the shape, for the sphere rather, beta naught is 1, beta 1 is 0, and beta 2 is 1. Therefore, the chi of S2 now will be the summation. So minus 1 raised to power k. So minus 1 raised to power k. So here you have 1 minus 0 plus 1. And that gives 2. For the torus, you have 1, 2, 1. So you have 1 minus 2 plus 1, which gives 0. Therefore, the Euler characteristic chi of S2 is 2, chi of T2, which is a torus, chi of a sphere is 2, chi of a torus is 0. Since Euler characteristic is a topological invariant, then the chi of S2 not being equal to chi of T2 implies that the sphere and the torus are not homeomorphic. They are not topologically equivalent. So the genus connection then is for a closed orientable surface of genus G, this genus connection. So chi is 2 minus 2G. So for the sphere, G is equal to 0. So x is equal, chi is equal to 2. For the torus, G is equal to 1. So chi is equal to 0. So for a double torus, G is 2. So chi is minus 2. So Euler characteristic therefore provides a compact numerical summary of important topological information like that. So we can also do that. So we just do a simple Python code. We define the function Euler characteristic, taking the Betti numbers. So the Betti number is k, right? Betti number k beta k. So minus 1 k beta blah blah. And then for the sphere, you have the Betti numbers 1, 0, 1, the torus 1, 2, 1. You put it all together, you get the Euler characteristic for the sphere to be 10, and that of the torus to be 0. Then we can also compare surfaces of different genuses, of different genus. Well, genus in range 5. So chi is 2 minus 2 genus. So if we print the genuses like they're just taking the value. So starting from 1 all the way to 4. So 0 to 4 rather. So if you run this now, for genus 0, Euler characteristic is 2. For genus 1, Euler characteristic is 0. So you have 2, 0, minus 2, minus 4, minus 6 like that. This illustrates how algebraic topology converts geometric intuition about holes and handles into computable invariants. So we have as the master summary of this whole story. Topology studies properties that remain unchanged under homomorphisms and continuous deformations. So the 6 major properties considered here are connectedness. Connectedness asks whether a space consists of one piece. A connected space cannot be separated into two non-empty disjoint open sets. Path connectedness is stronger. Any 2 points can be joined by a continuous path. Then you have holes now. Holes represent non-trivial topological structures that cannot be removed by continuous deformation. Betti numbers provide a systematic way to count holes. So you have beta naught, number of connected components, beta 1, number of independent one-dimensional holes, beta 2, number of independent two-dimensional holes. Then you have the dimension itself. Dimension describes the local number of independent directions. Examples include dim S1, which is 1, dim S2, which is 2, dim T2, which is 2. So dimension is an important topological invariant. So dimensions are easy to identify. Once you can see the S1, S2, T2, R, so the power just tells you what the dimension is easily. Then for the boundary identifies points where a space locally looks like a half space rather than the ordinary Euclidean space. So for the disk, the boundary of a disk is a circle. For the sphere, the boundary of a sphere is 0. For the torus, there's no boundary for the torus, also just like a circle, like that. Then we talk about orientability. Orientability asks whether a consistent orientation can be maintained throughout a space. Examples, for a sphere, it is orientable. Torus is also orientable. Möbius strip is not orientable, though it looks like a cylinder, which is equally orientable. The Möbius strip fails because traveling once around it reverses local orientation. Then we have compactness. So compactness is a fundamental global property for subsets of the n-dimensional real number system. The Heinborough theorem states that a compact space, if a space is compact, it is closed and bounded. If a space is closed and bounded, then it is also compact. That's the Heinborough theorem. So compactness implies closedness and boundedness, and closedness and boundedness imply compactness. So examples, the closed interval 0, 1 is compact, the open interval 0, 1 is not compact, and the real number line is not compact. So the big picture we see in all of this is this. These properties give different ways to distinguish spaces. A useful checklist is connectedness, holes, dimension, boundary, orientability, and compactness. When comparing two spaces, ask, are they connected? Do they have the same dimension? Do they have the same boundary structure? Do they have the same hole structure? Are they both orientable or both non-orientable? Are they both compact or both non-compact? These questions form a practical first pass toolkit for recognizing whether two spaces could possibly be homeomorphic, meaning are they topologically equivalent? The deeper study of these ideas leads naturally to homotopy, fundamental groups, homology, cohomology, manifolds, Euler characteristic, classification of surfaces, algebraic topology. The central lesson is topology is not primarily concerned with how a space looks, but with the structural properties that survive continuous deformation. Yeah, because this has been such a lengthy one, I think, let me see if I can just talk about the answers without working it out. Let's see how this goes. So, but I mean, you can see the problems. The following problems reinforce connectedness and all the other characteristics. Non-repeat the worked examples from lessons. So, you have questions 1 to 3 right here. Questions 1 to 3, like this. Then you have 4 to 7, 4 to 7, like that. 4 to 7. Then 8 to 10. You can see 8 to 10 there. That's 8 to 10. Then 11, 11 to 13, 11 to 13, 14 to 16. So, I mean, I would have solved 16 if we had time, but it's been straight to the point. Suppose a closed orientable surface has genus G3. Calculate its Euler characteristic using it. Just put the G. So, how does its Euler characteristic compare with that of a torus? So, in this case, now you're going to get 2 minus 6, which is minus 4. So, for comparison, a torus has genus G equals 1, and then you get 0 for that. So, that's the genus 3 surface. So, this surface with genus 3, has Euler characteristic -4, while the torus has Euler characteristic 0. So the negative value reflects the increasing topological complexity as handles are added. For each additional handle decreases the Euler characteristic by 2. So hence, the Euler characteristic is -4 for the genus 3 surface, and chi equals 0. The Euler characteristic is 0 for the torus. So that's what I would have solved. Then you have questions 17 and 18. Then I should have solved 22, but I don't think it's a problem. Consider the comparison. I think you can just refer to the table. Comparing a sphere with a torus with a cylinder. This is a cylinder because this is a circle together with a line, So that's a cylinder. Then you have the Möbius strip. Construct a comparison table containing connectedness, dimension, boundary, orientability, compactness, and all of these things. So use the table to identify at least two pairs of spaces that cannot be homomorphic and explain which invariant distinguishes each pair. So, yeah, like that. So, of course, we know S2 is connected. A sphere is connected. The dimension is 2. It has no boundary. It's orientable. It is compact. The beta one is 0. And chi, the Euler characteristic, is 2. Then talking about a torus, it is connected. The dimension is 2. It has no boundary like a sphere. It is orientable. The compactness is compact. Beta one is 2, and the chi-score is 0. So I mean, if the torus is very close to a sphere, except that the Euler characteristic differs, as well as the number of independent one-dimensional holes. So holes basically make the difference between spheres and toruses. Then for a cylinder now, so it is connected. The dimension is 2. It is bounded by 2 circles, so it has boundaries. It is orientable. The direction does not change when you move. Try to take a trip around it. Then beta 1 is 0 and chi is 0 also. For the Möbius strip, of course, it is connected. It is connected. The dimension is 2. The boundary is 1 circle. It would have been like a cylinder if not that the ends are inverted, kind of. And then it is compact and all of that. So that's the deal there. So the easiest, so it's easy to say a sphere and torus are homomorphic, but they are not because of the hole in a torus, like that. So let me know how helpful this is for you, and if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. But if you haven't subscribed, this is a very good time to go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges that you find out when you click on join. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.